Hello, and welcome back to our second talk of TWIST 2023. This talk is being given by Dr. Eve Lanham, who received her PhD from the University of Michigan in 2022 and has been with TechX for a year and a half. She specializes in low-temperature plasma physics and most recently has focused on modeling inductively coupled plasmas. Welcome, Dr. Lanham.
All right, so for this talk, I'm going to give a general background of inductively coupled plasmas and why you want to use VSim to model them. Give an overview of our 2D implicit EM solver that we released that enables our ICPs to be modeled. And then we're going to give a brief discussion about power deposition as a function of neutral gas pressure and with some concluding remarks. Inductively coupled plasmas are one of the main types of plasma sources. As you can see here, this is a source that generates a plasma. And inductive really means the power is electromagnetically coupled into the plasma. So the discharge is electromagnetically driven. This works by supplying an external current to an antenna. Usually the antenna is external to the plasma as well. This drives a magnetic field and induces an electric field that goes to heat the plasma. Plasma heating is usually done through ohmic heating. This is where the electric field accelerates the charged electrons. And this energy is only transferred from the field to the plasma when electrons impact neutral or other species in the plasma. This is because it's an RF discharge and the oscillations will cancel over time. So you really need collisions to extract energy from the plasma. It's also typical to add a separate power source, like for a substrate or a wafer bias, to control the flux of the energy of ions for processing. So an inductively coupled plasma is usually used to generate the plasma, and then you have separate control using a bias. So why would you want to use particle and cell technique to model ICPs? Fluid-based approaches are typically done just because they're convenient. But one reason why you might not want to use a fluid is because the mean free path should be smaller than the mesh resolution. And having this occur means that the assumption breaks down when moving to lower pressure. So you need kinetic effects to resolve this when moving to lower pressure. And a lot of the times chambers are operated for at lower pressures. So why are fully kinetic approaches to modeling ICPs not more commonplace? One, the driving frequency is pretty low, meaning that you need to take a lot of time steps to resolve the speed of light on the mesh. And also time domain modeling is sensitive to noise, which is also another reason. So our solution to this is to use our new implicit solve in cylindrical coordinates and have a smooth turn on to avoid the noise. So for modeling ICP systems, we are looking at cylindrical coordinates, and we have two separate solves. We have an electromagnetic solve for the fields using our proprietary implicit solver. This takes antenna current and adds particle current to it and gives you solves for the induced electric field data, and you could VR and BZ along the way. In addition to this, we couple an electrostatic solve using solve of the Poisson's equation for a cut cell framework, and this gives us the electric fields in and out of the plane. When we have all the electric fields, we can interpolate E and B to particle position and do the typical particle push. Our field solves typically converge in fewer than 10 iterations, and we can use different solvers just because we put in the effort to make sure that the matrix is symmetric. This slide shows that our new implicit EM solver is stable, running for this simulation 20 time steps per RF period. If we were going to solve this using explicit instead of an implicit scheme, we would have to take about 5,000 times more time steps. Being able to achieve time steps larger than this is much better for speed, computational efficiency. So this is a slide that shows that our inductively coupled plasma example. It's based off of the GEC reference cell in an ICP configuration. Here we're just showing one turn of the antenna, and we released it with the chemistry from the Turner benchmark, which is electrons, helium, ions, and 6 collisional processes. The geometry is such that the symmetric axis is here, and we have several dielectrics, such as a window, which separates the antenna from the plasma. We have a wafer for processing, which we can collect statistics on. We have a bias electrode, which we can give an RF potential to. We have a ground shield and a focus ring and a wall gap. And that's basically the geometry. Here we're showing that the electron positions plotted forming sheaths here and here. And we're showing that electrons are heated closer to the antenna, primarily closer to the antenna. And all of this example is available through visual setup of VSim, and it's something that you can run on your laptop. For example, we set the plasma initial density to 5 times 10 to the 14th per meter cubed, electron initial temperature of 2.5 eV with ion temperature of 300 Kelvin. You have a 100 amp current put through this antenna at 100 millitorr. And with these cells, 10 particles per cell initialized, we run 2 RF cycles in about 10 minutes on a MacBook Pro. And that's 800 time steps per RF cycle. Here you can see that we're forming sheaths in about 1 RF cycle, and electrons are accelerated by E theta, causing local heating. Yeah. If we're looking at propagation of the induced electric field into the plasma, here we're showing this is the dielectric window, and we're looking at a slice of E theta. As you can see, into the plasma, it decays exponentially, which is correct. And that's why you get most of the heating near the window. If we're looking at the electric potential, similar slice here, showing the window here. We get a potential in the plasma that's very positive for these initial time steps, and sheaths form between the walls and the plasma. So this is exactly what you like to see with just a few time steps. You can also look at the probe data. So we see that E theta oscillates 2 full RF cycles, and it shows a stable ramped E theta, and while the electric potential kind of saturates in that time scale. Additional work we've done since releasing the example is adding multiple turns to and here we're looking at differences in potential with the gas pressure. So previous results I showed were at 100 millitorr, and now I'm showing 20 and 1 millitorr, the electric potential for, low electron density and a high antenna current. We see large spatial gradients in the potential for low pressure, and the collisions tend to smooth the potential. So you can see here, there's more of a gradient at lower pressure. If we're looking at the electric potential, this is with the probe. You can see for higher pressure, more collisions deposit more power, and it pulls out a high energy electron tail, which is more easily lost. So we saw that with just running 2 RF cycles, we can capture behavior such showing that the potential for 1 millitorr is going to be lower than 20 millitorr, at least at startup. So in conclusion, we introduced ICPs and motivation to use a kinetic approach for modeling. We showcased our implicit EM solve that is up to 5,000 times faster than resolving the CFL condition. I showed results from our example that's at 100 millitorr with 1 antenna turned, and it showed reasonable results for the electron temperature, ion temperature, potential, and E fields. We saw that sheaths were developed very quickly, and E theta propagated into the plasma as expected. And we also compared 1 and 20 millitorr with multiple antenna turns, showing that collisions smooth out the potential spatially, and there are clearly transients at low pressure. So with that, I'll take any questions.
And for questions, if there is the Q&A box on the bottom of your screen, if you type them in there, then we can go ahead and I will read them to you. All right. So the first question is electrons in low pressure ICPs are often in collisionless regime, like Godiac's experiment, such that the energy absorption is anomalous, collisionless. Are you able to access these regimes? And if so, have you seen collisionless features like non-monotonous energy absorption?
That is a very good question. And we are trying really hard to show these things. We can run, right now, we have particles interacting with a background fluid, and we can capture that effect, but we have not developed plotting mechanisms to make it look good and analyze those results. So those should be forthcoming and something we're looking forward to working on further.
Okay. Another question, what is the total simulation time?
So both of these, each one ran in 10 minutes. You can run it on a laptop. If you want to go to higher plasma density, you will have to run either bigger simulations or longer simulations. Depends on more on the plasma that you want to resolve than the electromagnetics.
Physical and micro, there was a clarification just saying physical and microseconds, I think, about the simulation time.
Oh, so we ran for two RF periods. An RF period's a fraction of a microsecond, 13.56 megahertz, just running two of those RF periods. That's the physical time that we've been running. Multiple RF periods.
Other questions? We still have time to take a few more if you want to take them in that box. And if you would like to evaluate this and try it out for yourself, you can request an evaluation VSim, whether you're a current customer or you've looked at us in the past. If you go onto the website at txcorp.com, there is a big button that says request evaluation. And if you do that, we can get a copy of the latest version over for you to try. Other questions? Maybe that's it for today. That may be all we have for today. Thank you so very much, Eve, for taking the time to do this for us. We are going to have a bit of a break. Our next talk will start at 11 a.m. Mountain Time. All right. I think we're good, Eve. Thanks so much.